Hello, pre-algebra students. This is Mr. Kraft coming to you from home. We just finished working on a whole bunch of stuff dealing with fractions, changing fractions into mixed numbers, vice versa, ratios and stuff. And now that we're finished with the fractions in Chapter 5, we're starting into Chapter 6, which is more fractions. But that's okay, because fractions are your friends, right? Fractions are your friends. Right? Well, maybe you'll disagree with me on that, but they are very important. So what I'm going to do, I'm going to keep this video fairly short. What I want to try to do is get through Chapter 6. I'm probably not going to do each section bit by bit by bit. I want to hit the highlights. And we want to get to the point where we are working algebraic equations using fractions. So previously, you've done things like this. 3x plus 2 equals 5. Solve for x. What we want to be able to do is 1/3 x plus 1/2 equals 1/5. How do you work something like that? And trust me, it's not as bad as it looks. There's techniques for that. But we need to kind of review everything before we can get there. So this is going to be just touching base, kind of a review. You've all had your fraction skills for several years in a row, and we've been reviewing the basic stuff. So what I'm going to talk about today is your basic arithmetic of fractions. We're going to talk about addition and subtraction of fractions and mixed numbers. Okay, so you know if you have 1/5, 1/5, plus 3/5, 3/5, that is going to simply be 4/5. It is the numerators only that you add. The denominator does not change. You know, I have had 20-year-old students in college do this. 1/5 plus 3/5 is 4/10, because they said 1 plus 3 is 4, and 5 plus 5 is 10, and that is just wrong, wrong, wrong. I cannot mark it out enough to say how wrong it is. It is wrong, 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 it is wrong. The word numerator should make you think of number or numeral, which essentially means the same thing. And that's exactly what it is. A numerator counts how many of these guys we have. You cut a pie into 5 pieces. And one of you has 1 piece. And another one of you has 3 pieces. How many pieces do you have all together? 1, 2, 3, 4. That's what it means. But the size of the pieces does not change, fifths or fifths. So when you add or subtract, your denominators are never going to change, with the exception of if I had, say, just the simplest example, 1/9 plus 2/9 is 3/9. But 3/9, and we've talked about reducing the lowest term already, it should be obvious that 3/9 is not in the lowest terms. So if you left an answer like that, I would take credit off. Because you remember I've said this, when do you reduce to lowest terms? And the answer is always. Are there times you don't want to reduce to the lowest terms? No, always. So you say the GCF, the greatest common factor, the biggest number that will go into both of these, which is 3. 3 goes into itself once, and 3 goes into 9 3 times. So lowest terms, that is the only situation where your denominator can change. In all other cases, your denominator is never going to change. Okay, so then if you are adding unlike denominators, you have to make them be common denominators. And the way you see if they're common denominators is you say, what is the least common denominator? And this is not an unknown term for you all guys. Known to his friends as LCD, which is the same thing actually as least common multiple. Known to its friends as LCM. For 5 and 7, they are relatively prime. Nothing goes into both of them but 1. So the way to get the LCM or LCD is just 5 times 7, which is 35. With each of these, then, you say, what times the denominator will give me the common denominator? The answer is 7 here. And whatever you multiply the denominator by, you must multiply the numerator by also. 3 times 7 is 21. 7 times what is 35? The answer is 5. So you say 1 times 5. 1 times 5, there's the hard part, 5. Now, add the numerators. 21 plus 5 is 26. 26 over 35. Can that be reduced? No. 26 is divisible by itself and 13. 35 is divisible by 7 and 5, so you stop there. Easy peasy. With something like, say, I don't know, 1/8, 1/6, well, you could say 8 times 6, which is 48. But that's not actually your least common denominator or multiple. You could say your times table, 6 times 1 is 6, 6 times 2 is 12, 6 times 3 is 18, 6 times 4 is 24, 6 times 5 is 30, etc. 8 times 1 is 8, 8 times 2 is 16, 8 times 3 is 24, 8 times 4 is 32, 8 times 5 is 40, blah, blah, blah. And then you would see the first number that pops up on both lists is 24. So it's the least common multiple. Multiples are just times tables. A number times 1, times 2, times 3, times 4. And we only go up to 12 in what we teach, but it could go on forever. So you can always find an LCD or LCM, because it's the same thing, by writing out the times tables. And obviously the problem with that is it's long and tedious. So I may do a separate video about this. I don't know. I believe I've talked to you about this, or at least I've touched on it. But basically what you would do is, if you don't see that it's 24, I mean, it's not hard to see that the LCD for 8 and 6 is 24. If you don't see it, which is the best way to do it, and if you don't want to write out the times tables, which frankly I would not recommend, what you do is you take each of your denominators and you do a factor tree, a prime factor tree. So 8 is 4 times 2. Essentially what you're doing is you're just taking it down until you end up with prime numbers. So 2 and 2 and 2 are prime. 6 is even easier than that, 3 times 2. Then we see what is shared. What is shared? So I say 2 is shared, because there's a 2 at the bottom, and you're looking at the bottom of these trees, people. 4 is not at the bottom. It's not prime, so I'm not concerned with it. All we're looking at is the bottoms of the roots of the trees. The 2's are shared. They're matched. So since they're shared, I count it one time. Because if you're sharing something, it's the same thing. It doesn't count twice. If you're both sitting at the same table, you share the table. That doesn't mean there's two tables. Times. Now I have to say what is not shared. These are not shared. I mean, they're both in the same tree, but the sharing has to be from one tree to the other. You can't share with yourself. So I have to put 2 more 2's in to account for these guys. 3 is not shared, so I have to stick that in. Now, multiply it all and see what I get. 2 times 2 is 4. Times 2 is 8. Times 3 is, ta-da, 24. Okay. So, I do the same thing I did before. What times 8 gives me 24? And I multiply that in both the bottom and the top. What times 6 gives me 24? I do that in both the bottom and the top. Therefore, 3 over 24 plus 4 over 24 is 7 over 24. 7 will not go into 24, nor does anything go into both of them except for 1. So I stop. Okay? This, for you guys, should just be a review. You've had this in the 6th grade. You've had this in the 7th grade. I know you had the 7th grade because I had y'all then. This should be a review. That's why I'm going fairly fast. Now, in the comments you give on the Google Classroom, if you're having trouble with this, I can go over more detail, make more videos, whatever. But for this, I'm going through it fairly fast because this is not new, or it shouldn't be. Subtraction is the same thing. 5/6 minus 1/6 is just 4/6, but 4/6 is not in lowest terms. 2 goes into 4 twice. It goes into 6 3 times. So that would not be right. You'd lose points. This is correct. That's fully correct. Likewise, if you had 4 over 8 minus 1 over, well, that's a bad example. That would give you 0. If you had 5 over 8 minus a half, this case, 8 itself is the LCD. You would not want to say 2 times 8, 16. 8 itself already is the LCD because 2 goes into 8 and 8 goes into itself. Well done. So since 8 already is the LCD, the 5/8 doesn't change. Doesn't have to change. The half does, though. 2 times what is 8? The answer is 4. 1 times 4 is 4. So 5/8 minus 4/8 is 1/8. Okay? That's all that happens there. Okay. Now, what I want to look at now is addition and subtraction of mixed numbers. There's 2 situations that can occur. One is where there's no borrowing and no carrying from the fractions. So 8 1/3 plus 7 1/2, for example, and maybe I'll put it in a different color so you can see I'm doing something different. 5 4/5 minus 3 1/2. So what happens in these guys, the whole numbers do the whole number thing and the fractions do the fraction things, and they don't really get in each other's way. So 2 and 3 are unlike denominators, so I have to make them common. And hopefully you can see easily that the common denominator for 3 and 2 is 6. So then I say, what times 3 gives me 6? Multiply the numerator, I get 2/6. What times 2 gives me 6? Multiply the same thing times the numerator, 3/6. 2 6 and 3 6 are 5 6. 7 and 8 are 15. 5 6 does not reduce. End of story. Done. Ding, ding, ding. Same thing for here. 5 and 3 do their own thing. 10 is the LCD for 5 and 2. 5 times 2 is 10, so I have to say 4 times 2 is 8. 2 times 5 is 10, so I have to say 1 times 5 is 5. 8 tenths minus 5 tenths is 3 tenths. 5 minus 3 is 2. Ding, 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 ding. Okay. So in this case, with addition or subtraction, the whole numbers don't get involved. They do their whole number thing, the fractions do their fractional thing, and everybody's happy. But it's not always quite that way, so let's look first at carrying. So carrying. So let's say you have 4 2/3 plus 7 4/5. Now, just conceptually, 2/3 and 4/5. That's a pretty crummy looking circle. I can do better than that. Well, it's not much better either, is it? Not perfect, but it'll do. 4/5. Just looking at it visually, if I put all the shaded pieces together, I'm going to end up with more than a whole pie. I'm going to end up with 1 and some other pieces left over. So that's really what carrying is saying. My fractions are going to make more than a whole, and that's going to have to be represented. So I start off the same way I did before. I'm going to have the whole numbers doing the whole number thing, and the fractions doing the fraction thing. 3 and 5 have 15 for their common denominator. So 3 times 5 and 2 times 5, 10/15. 5 times 3 and 4 times 3, 12/15. So that's going to give me 10/15 plus 12/15 is going to give me 22/15. Now, if I added the 4 and the 7 and got 11 and 22/15, it actually hurts to look at that. It is not only an improper fraction, it's not only a mixed number, it's a mixed improper fraction, and we do not do that. So what I'm going to have to say is this guy here is an improper fraction. Now, as you will see later on, possibly in this class, or if not in this class, you'll see it in Algebra 1, there are some times that it's good to leave an improper fraction alone. This is not one of those times. So, as you recall, we did this not long ago. You take the numerator, which is the top number, divide it by the denominator. So 22 divided by 15. 15 goes into 22 one time only, and 22 minus 15 is 7. So your quotient, the answer, becomes your whole number. Your remainder becomes your numerator, and your divisor, which was originally the denominator, stays the same. Your denominator, just like what we talked about earlier, unless something could be reduced, like if that would have been 5/15, it would reduce, but usually the denominator is going to remain unchanged. So now the 7/15 is good to go. But the 1 has to go over and play with the whole numbers because it's not a fraction anymore. You carry it. 1 plus 4 is 5. 5 plus 7 is 12. That is the final answer. Okay. Borrowing. I've got good news and bad news. And I'll give you the bad news first and then the good news. Borrowing is probably the hardest thing you'll do in fractions. In this class anyway. That's the bad news. The good news is, if you can do it, then everything else is easy afterwards. So let's look at this. Let's talk about borrowing with regular numbers first. So let's say I had 72 minus 18. Well, I cannot take 8 from 2. So I borrow from the 7, and I put a 1 with the 12. Actually, I just lied to you. That's not a 7. This is not a 1. That's not a 6. Actually, 72 means 7 tens and 2 ones. So this is actually 70, and that's 2. I really have 60 left, and I borrow 10. 10 plus 2 is 12. But the easier way to say it is we say I take 1 from the 7 and leave it a 6. So just as long as you're aware of what it really is, we won't worry about the technicalities. 12 minus 8 is 4, and the remaining 6 minus 1 is 5. Now, let's say we had 5 1/3 minus 1 4/5. Now, it should kind of sort of be obvious that there's going to be a problem here. 1/3 is very obviously, or I hope it's obvious, very obviously smaller than 4/5. I mean, you could draw a diagram and see that. This is a third. This is a horrible drawing. But even with a horrible drawing, you can see that 1/3 is very obviously smaller than 4/5. But we're not going to address that just yet. First, we have to get common denominators, which is 15. 3 times 5 is 15. We have to convert everything. 3 times 5, 1 times 5, 5/15. And 5 times 3 and 4 times 3, 12/15. So we have 5 5/15 minus 1 12/15. And now it is very clear 5/15 is smaller than 12/15. So we have to borrow. Now, what a lot of students start off doing here is they say borrow 1 from the 5, leave a 4, and make that 15/12. Seems reasonable. It is not right. Oh, not even close. Nope, 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 nope. None of that. See here, that worked because I took 10 from the 70, left 60, 10 plus 2 is 12. When I borrow from the 5 and I leave a 4, so that much is right. This 1 I borrow is not a 10 like it was over here. It is actually a 1. So I can't say 10 plus 5 is 15. I'm not doing that. This is just a plain old 1. Because see, here you have the 10's place and the 1's place. All I've got is the 1's place here. There's no 10's place. It's just 5. 1 has to be changed into 15ths because this is the 15ths place. Because, well, duh, it's got 15ths. Fortunately, that's easy, though, because anything over itself equals 1. So 1 is 15 over 15. Just like it would also be 17 over 17, or 1,000 over 1,000, or 2 over 2, whatever. 15 plus 5 is 20. 20/15. And now we've got 4 left. Now, I said just a few minutes ago that a mixed improper number is a horrible thing, and I'm not taking that back, but we do have it temporarily here, just temporarily. Also, let me show you the way to kind of fudge on this. I wanted you to see this, so you know why. But the shortcut is just take the 15 and add it to the 5. Boom, got 20. So that's how it works. 20/15 minus 12/15 is 8/15. 4 minus 1 is 3. 8 over 15 does not reduce. Boom, you got it. I hope that's not too obscure. Let me do one more example like this. Say we had 17 1/7 over, oh, I don't know, 8 1/3. Subtract. Well, we start off 17 and 8. It's not changed. 7 and 3, the denominator is going to be 21. Because nothing goes into 7 and 3 except for 1, so you have to get the LCD by multiplying. So the LCD equals 7 times 3 equals 21. 7 times 3 and 1 times 3, because remember, whatever you multiply the numerator by, the denominator by, rather, you multiply the numerator by. Same thing here. 7 is obviously bigger than 3. And now I'm going to go ahead and do the fudge. I borrow from the 17, leaving 16. Then I just say denominator plus numerator, 24. Boom, easy as that. No thought involved at all, hardly. And the 8 and 7/21 does not change. 24 minus 7 is going to be 17. 16 minus 8 is 8. 17 and 21 are relatively prime. Nothing goes into them both. Ta-da! That's your answer. Okay. So I want to give you a few problems to practice on this. This is not a horribly difficult thing. I really don't think it is. You just need to see what's going on with it and be careful that you do it right. I'm going to wind this presentation up for now, and I will talk to you the next time. See you later. Bye.